स्टार्ट करो मैडम.
Good afternoon, students. Welcome to the TREI webinar chemistry class. This is Naziya Sulthana, PGT Physical Science from Vikarabad. Today we would be learning the chapter that is solutions based on IIT and NEET point of view. Okay. So we can expect two questions. Okay, two questions are expected, both for IIT as well as NEET. So please do not think that only two questions, but each, as we say, every drop will make an ocean, right? So in the same way, each and every question would be making up your IIT or the NEET question paper, right? So please concentrate and try to learn, practice the formulae. And it is a very important and simple topic where you can score. So we would be going to the gist of the chapter. Yeah. So we will see the summary of the chapter. So solution. Okay. What is a solution? Solution is nothing but it is the homogeneous mixture of two or more components. Okay. Homogeneous mixture of two or more components is called as solution. And the substance taken in the lesser quantity is called as solute. The substance taken in the larger quantity is called as solvent. Okay. So when the solute thoroughly gets dissolved in the solvent, it gives us the solution. Okay. And another way of saying, defining the solute is the substance which gets dissolved is the solute. The substance which is able to dissolve as another substance, that is called as solvent. Okay. So now we will see different types of solutions based upon the amount of the solute present. Okay. So the solutions are classified as unsaturated, saturated solutions and supersaturated solutions, right? Supersaturated is nothing but it is unstable solution. So for that reason, it is not mentioned over here. Yeah, you can see unsaturated solution. So again, they can be further classified as dilute and concentrated solutions. Dilute solution is the one which has lesser amount of solute. Okay. Whereas coming to the concentrated one, it is the solution which contains more amount of solute. For example, we will be preparing the solution using 5 grams of solute and another solution we are using 10 grams of solute. So here 10 grams is more, that is the concentrated solution. Whereas the solution which contains only 5 grams of solute, that is a dilute solution. Yeah. Next, coming to the saturated solution. What is saturated solution? Saturated solution is the one which cannot dissolve any more solute. Okay, at a given temperature. That is the saturated solution. Next, we can say that sometimes the solute can be soluble, it cannot be soluble. Okay, so this is based upon the ability of the solute to dissolve. Right. Next, another way of classifying the solutions is based upon the physical state of the solute and solvent. Right. So if the solvent is a gas, we call it as a gaseous solution. If the solvent is a liquid, we call it as a liquid solution. And if the solvent is a solid, we call it as a solid solution. So this is based upon the type of the solvent. Again, the physical state of the solute can vary, yes or no. The solute can be solid in state, liquid in state, or gaseous in state. So based on that, let us see what are the examples we are going to see. Okay, a gas can be dissolved less, that's nothing but the air. These examples are very, very important. So please learn the examples. Next, gas can be present in the liquid. Example, soda water. What is the gas used there? Carbon dioxide. Gas present in the solid. So occlusion, the principle is called as occlusion. Example, occluded hydrogen or hydrogen in palladium. We know that transition elements, their interstitial spaces can accommodate hydrogen. They can give place for hydrogen. So hydrogen would occupy their interstitial spaces. Okay, so such kind of hydrogen is called as occluded hydrogen. So hydrogen in palladium, that is an example of gas in solid. Okay, next is liquid present in the gas, nothing but water vapor, humidity in air. Next, liquid in liquid, that is alcohol in water. Liquid in solid, mercury in gold. We know that mercury is the liquid metal, right? Mercury in gold. So whenever we see that, we call it as an amalgam. Okay. Next, solid present in the gas. Example, camphor. Okay. Camphor, what is the physical state of camphor at room temperature? It is gaseous. Sorry, it is solid. But upon sublimation, it is getting converted into the gas. So camphor in air, it is an example of solid in gas. Okay. Next, solid in the liquid. Best example, our tea, boost, lemonade. We are just dissolving sugar in the water, right? Next, solid in solid. Example, alloys. What are alloys? This can be asked as, this is an important question for both the IP as well as for your competitive exams. Alloys are nothing but they are the homogeneous mixtures of two or more metals. Okay. Next, some more examples you can see here. Gaseous solution. Yeah, what is a gaseous solution? The solution in which the solvent is a gas. Okay. Example, mixture of oxygen and nitrogen. Liquid in the gas. Chloroform mixed with nitrogen. Okay. Chloroform, what is its physical state at room temperature? It is a gas. Sorry, it is a liquid, but it is a volatile liquid. That means it is taking up the heat from the surrounding and getting vaporized. Okay. This is an example of liquid in the gas. Okay. Next one is solid in gas. Yeah, just now we have seen. Only here thing is one or two examples are different. Okay. So camphor in nitrogen gas. Next, liquid solutions. So liquid solution means solvent is the liquid. So gas in liquid is oxygen dissolved in water. So this is again important because oxygen present in the water is the source of oxygen for the aquatic organisms. Okay. And liquid in liquid, ethanol in water, solid in liquid. So these are the common examples. Just now, whatever we have seen over here, the same examples are being repeated. Okay. Yeah. Next is types of solutions based on the solvent used. So we know that water is the universal polar solvent, right? And apart from water, even alcohol is being used as a solvent. Next to water, ethyl alcohol is used as the solvent. So if water is used as a solvent, we call it as an aqueous solution. Example, saline. Okay, saline is 0.9% NaCl solution. Whereas tincture of iodine, okay, they will not directly give you what is an alcoholic solution. They can give you tincture of iodine can be an example of dash type of solution they can ask, right? So tincture of iodine is an example of alcoholic solution. Here iodine is the solute and alcohol is the solvent. Yeah. Next, let us see the differences between suspension, colloidal solution and a true solution. True solution can also be called as crystalloid. Okay. Yeah. So we will see what are the properties. So some of the properties are, okay, particle size. If the particle size of the solution is greater than 100 nanometer, we call it as a suspension. If it is from 1 to 100 nanometer, it is a colloidal solution. Lesser than 100 nanometer, it is a crystalloid or true solution. Okay. Next, coming to filtration separation. Okay. Yeah, coming to the filtration separation. So the suspension, the particle size is large, so they can be cannot as the particle size is large, okay, the components cannot pass through the pore size, so they can be separated. Whereas colloidal solution, it is not possible because the particle size is lesser, so it is easily able to pass through the pores used in the filter. Okay. Whereas coming to the true solution, even the components of a true solution cannot be separated by filtration because the particle size is small. So whenever we are just filtering out, the particles will easily pass through the filter. Yeah, coming to the settling of particles. In the case of suspension, because the particle size is large, they are affected by the gravity and hence the particles will settle down. Whereas in case of colloidal solution and true solution, the particles will not settle. Okay. The particles of a colloidal solution will settle provided we centrifuge it. Okay. So the particles of a colloidal solution can settle upon centrifugation. Okay. Next, coming to the appearance. The appearance of a suspension is opaque. Okay. Whereas the appearance of colloidal solution and the true solution is transparent. Okay. Next, coming to the other property, that is Tyndall effect. So what is Tyndall effect? Nothing but the scattering of light, right? So the particle, because the particle size is larger in the case of suspension and a colloidal solution, the particles are able to scatter the light. Whereas in the case of a true solution, because the size is small, they are unable to scatter the light. Okay. For that reason, they do not show the Tyndall effect. Next, coming to the another property, that is diffusion of particles. Okay, so the particles of a suspension do not diffuse, whereas the particles of a colloidal solution, they diffuse slowly. Whereas the particles of a true solution, they diffuse rapidly. What could be the reason? Particle size. Okay, next is coming to the Brownian effect or Brownian movement. So what is Brownian movement? Zigzag motion of the colloidal particles. Okay. So the zigzag motion is because of collisions between the particles. That is called as Brownian movement. So Brownian movement is exhibited by colloidal solutions, whereas it may or may not be shown by the suspension and the true solution. Okay. Next, another very important feature is nature. Okay. A true solution, only a true solution is homogeneous, whereas both the suspension and the colloidal solution are heterogeneous. And here one thing what we have to know is a colloidal solution is appearing homogeneous, but actually it is heterogeneous. Heterogeneous solution appearing as homogeneous. So if we want to observe the two different, what do you mean by homogeneous and heterogeneous? If you are able to see only one phase, that is homogeneous. If you are able to see two different phases in the sense state of matter, if you are able to see two different states, we call it as heterogeneous. Okay, for example, oil and water, we are able to see two different layers, that is heterogeneous. Okay, whereas if you put small pebbles in water, we can see that two different phases, so that is heterogeneous. Okay, so true solution is homogeneous, whereas okay, whereas a colloidal solution is heterogeneous but appears homogeneous. Example, best example is milk. Yeah. Next, coming to another important topic, that is the methods of expressing concentration. Okay, so first we need to know what is concentration. Concentration of the solution means the amount of solute present in the given volume of solution. Okay, so there are various methods. So what are those? Let us see. Okay, mass percentage or weight by weight percentage. It is nothing but the mass of a component of the solution by total mass solution into 100. You please practice all this formulae till you get. You should be able to write by yourselves. Okay, all the methods of concentration. Next, coming to volume percentage, volume of the component by total volume of the solution into 100. Mass percentage and volume percentage, they do not have the units. Reason? Because of the same, it is the ratio of same components, same units. So the units get cancelled. Next, coming to weight volume percentage. Okay, or weight mass by volume also we can see. So mass of the solute by 100 ml of solution. Okay, mass of solute present in 100 ml of solution is called as mass by volume or weight volume percentage. Next, ppm, parts per million. Okay, so this is here one of the important bit that can be asked is, this method of concentration is used to express the concentration of pollutants. Okay, ppm means the number of parts of a component present in total number of parts of all the components into 10 to the power of 6. Okay, 10 power 6 is what is 1 million, right? Next, coming to the mole fraction. Yeah, again, this mole fraction also doesn't have the unit because it is the ratio of similar quantities. Okay, so number of moles of a component to the total number of moles of all components. That is what is mole fraction. Okay, so here, whenever you are going to solve the numericals based on mole fraction, first thing what you have to know is you have to thoroughly know the atomic weights of the elements. If you know the atomic weights, you will be able to calculate the molecular weights. Again, while calculating the molecular weights, you have to know the correct formula of the compound. Okay, until and unless you know the correct formula, you will not be able to do it. Okay, so what I mean to say is, you please practice all the atomic weights of the at least first 20 elements, and some of the important metals like iron, cobalt, copper, okay, manganese, those you practice, chromium. From those only, mostly it would be asked. And if it is unknown compound, they would be giving the formula in the question itself, right? Even if the formula is given, you should know the correct atomic weight, then only you will be able to calculate the correct molecular weight. When we are able to calculate correct molecular weight, we will be getting the correct number of moles. So it is all interdependent, right? Next, coming to the molarity. So molarity is nothing but this is also one of the method of expressing concentration, where we are taking the number of moles. It is the ratio of number of moles of solute present in given volume of solution expressed in liters. Okay. Next is another method is molality. So molality is nothing but it is the number of moles of solute present in given volume mass of solvent. Here molality is mass of solvent. This you have to please make a note of. Okay, and here we are as we are learning this chapter, molality is very important because it is going to be expressed again in terms of elevation in boiling point, depression in freezing point. Okay, those two depend upon the molality, and molarity, osmotic pressure depends upon molarity. Okay, so please go through these formulae. Next, coming to the another topic, that is solubility. So what is solubility? Solubility is nothing but the maximum amount of substance that can be dissolved in an amount of solvent at a given temperature. Okay, so temperature plays an important role. Yeah, let us see the factors affecting solubility. So the factors affecting the solubility are, okay, temperature. So as the temperature increases, solubility would increase. Okay, best example, sugar getting dissolved in hot milk, cold milk. Where will the sugar dissolve faster? In hot milk, because of high temperature. Next, coming to the particle size. Greater the particle size, lesser is the solubility, or lesser the particle size, greater is the solubility. Next, or faster is the dissolution, we can say. Next, mixing, okay, or stirring. So when we stir, easily the substance gets dissolved. Okay, and coming to the last but not the least, that is the nature of the solute and solvent. So we know that it is best told by one of the simple sentence, that is like dissolves like. That means polar compounds are soluble in polar solvents, and non-polar substances are soluble in non-polar solvents. Okay. Yeah. Next is solubility of liquids in liquids. Okay. there are, see, when all the liquids soluble? No. For example, if we take water and oil, they're not miscible. They're not mixing thoroughly. Such liquids are called as immiscible. Whereas if you're talking about the liquids which get mixed thoroughly, we call it as miscible liquids. Okay. And as we are saying, it is the solution. That means if we are mixing two liquids, those liquids should be thoroughly miscible. They should be thoroughly mixing. Then only we get the homogeneous mixture. Okay. Next, we can see here upon the solid, we are having three types of solutions. That is unsaturated solution, saturated solution, and supersaturated solution. And unsaturated is the one which can dissolve some more amount of solute. Saturated cannot dissolve any more solute at a given temperature. And whereas supersaturated, it becomes unstable and it is prepared at higher temperature. And upon cooling, excess of solute would crystallize out. Okay. And another important thing I would like to say here is a saturated solution can be converted into unsaturated by two methods. It is either by increasing the temperature or else by adding some more solvent. So when we add some more solvent or else increase the temperature, then the saturated solution becomes unsaturated. Okay. Yeah. Next is types of solutions based on concentration. If the number of solute particles are more in a given volume of solution, we call it as concentrated. If the solute particles are less in a given volume of solution, we call it as a dilute solution. Okay. Next, coming to the solubility of gases in liquid. Yeah, gases can dissolve in the liquids. So that is also a kind of solution only, right? So now you see, gas is dissolving in the liquid. So when can a gas dissolve in the liquid? When the pressure on the gas is more. If pressure is more, the gas molecules will come closer, they interact with the liquid and they can get dissolved. Okay. So remember, the solubility of a gas depends upon the external pressure. Okay. As well as it also depends upon the temperature. So if the temperature is high, the gases already have high kinetic energy. And when we are increasing the temperature, they further gain the kinetic energy and they will move away. Okay. So if we want to dissolve the gas in a liquid, what we have to do? Lower the temperature, increase the pressure. Okay. Hope you are understanding it. Yeah. Next, coming to the solubility. Yeah, this relation between the solubility of the gas and the liquid was given by a scientist, that is Henry. And Henry's law states that the solubility of any gas, okay, increases as the external pressure is increased. That means as we increase the pressure, the solubility would increase. Okay. And he has given a relation. PA, let PA be the pressure of the gas. Okay. This is directly proportional to the mole fraction of the gas. Okay. So you can see here, PA is directly proportional to the mole fraction of the gas. PA is equal to KH into XA. This is mole fraction, right? So K is called as Henry's constant for specific gas, and XA is the concentration of moles dissolved in the liquid, and PA is partial pressure of the gas. Okay. Next, coming to the applications of Henry's law. So Henry's law is very, very important. It has some of the important applications. Okay. One of the application is dissolution of carbon dioxide to prepare softer drinks. Yeah, carbonated drinks. They contain carbon dioxide. That means carbon dioxide is dissolved in the liquid. Okay. Next, the scuba divers, they carry the respiration tanks diluted with helium. Okay. Otherwise, what happens if helium is not present? Nitrogen would dissolve in the blood. Nitrogen has more solubility. And when the person comes up, okay, because of excess pressure inside, the nitrogen would come out, right? So that would cause air bubbles in the blood. That is what is called as bends. Okay, that might be serious enough to cause death. Okay, for that reason, the scuba divers, they carry the respiration tanks diluted with helium. Okay, next, another application is the persons whoever climb, mountain climbers. Okay, they have to carry the respiration tanks. Okay, they have to carry oxygen because as the height increases, the pressure decreases. Okay, so the amount of oxygen also would be lesser, right? For that reason, they have to carry the oxygen. Okay, next, coming to the another topic, that is evaporation. Okay, we know that evaporation is nothing but conversion of a liquid into the gaseous form at room temperature. That is called as evaporation. Whereas boiling is conversion of a liquid to the gaseous form only, but upon heating. There is a difference between evaporation and boiling. Okay, evaporation causes cooling effect, boiling causes heating effect. Okay, and evaporation, no need to provide external heat. For boiling, we have to heat. Okay, and evaporation surface phenomenon, boiling is a bulk phenomenon. So these are the major differences between evaporation and boiling. Yeah, next, coming to the factors affecting evaporation. So the factors affecting evaporation are temperature, surface area, humidity, and wind speed. Okay, greater the temperature, faster is the evaporation. Greater the surface area, faster is the evaporation. Greater the humidity, lesser is the evaporation. And greater the wind speed, faster is the evaporation. Okay. Next, coming to the vapor pressure and boiling. Yeah, what happens just now we have discussed. Evaporation means vapors would be there, right? So these vapors will as the vapors are moving away, they can again condense into the liquid. Okay. So when at a particular stage, rate of evaporation would be equal to the rate of condensation. What is condensation? Conversion of vapors into the liquid. Okay, evaporation is liquid into the vapor. Okay, so at a particular stage, what would happen is, okay, rate of evaporation is equal to rate of condensation. Okay, and that is called as saturated vapor pressure. Okay, the gas molecules would be exerting the pressure on the surface of the liquid. That pressure is called as vapor pressure. Okay, so what is vapor pressure? It is the equilibrium pressure of vapor above the surface of the liquid. Okay. Next, coming to the mixture of volatile liquids. So now what we are doing is mixing two liquids. And two liquids are volatile in nature. Volatile means which can easily get converted into the vapor phase. When can the liquid get converted easily into the vapor phase? When it has low boiling point. Okay, so you can see here, when we are mixing two volatile liquids, they get vaporized easily, right? So now these two liquids are going to contribute to the vapor pressure of the solution. When we are mixing two liquids, it will definitely give us the solution. Now the vapor pressure of the solution is because of both the liquids. So what can we say? The pressure is because of the solute as well as the solvent. Okay. So let the solution A be liquid A be solute, the other liquid would be the solvent. So because of both the liquids, we are going to see the vapor pressure. And how can we calculate the pressure of the liquids? Pressure of the pressure because of individual liquid is called as partial pressure. Okay. So P total is nothing but the pressure of the solute, pressure of the solvent. So pressure of the solute is nothing but it is the product of mole fraction of the solute into, okay, vapor pressure of pure solute. Okay, and yeah, you can see here, when the substance is made in the solution, right? Okay, when the substance present in the form of a solution, in the solution, the pressure due to the solvent is nothing but it is the product of mole fraction of the solvent and vapor pressure of the solvent in pure state. Okay, so this is the pressure because of the solvent. This is the pressure because of the solute. And when we are summing up these two, we get the total pressure. Okay. Yeah. Next, coming to Raoult's law. So that just now what we have seen, the vapor pressure was because of both the liquids in the case of volatile liquids. Now we are going to add one non-volatile substance to a volatile substance. What will happen if the solute is non-volatile? The solute will not vaporize. Only the solvent will vaporize. So as a result, what will happen? The vapor pressure of the solution will decrease. The decrease in the vapor pressure of the solution, okay, is given by, it is well explained by Raoult. Okay, so he has given a statement. That is what is called as Raoult's law. So what does it say? We can say, okay, the relative lowering of vapor pressure of a solution, okay, relative lowering of vapor pressure of a solution is directly proportional to the mole fraction of the solute. Okay, that means if you are dissolving more amount of solute, lowering would be more. Okay, if you are dissolving lesser amount of the solute, the lowering would be lesser. Okay, yeah, you can observe here. Lowering of vapor pressure. Okay, when a non-volatile solute is dissolved in volatile solvent. Okay, only because of solvent only we are going to see the vapor pressure. Okay, so let PA be the vapor pressure of the solution, right? And P dot A is the vapor pressure of pure solvent, and XA is the mole fraction of the solvent, okay, in the solution. Next, yeah, you can see here this PA is nothing but vapor pressure of the solvent in the solution. Okay, P naught A is the P naught A, this is the vapor pressure of the pure solvent. Okay, so this is given, right? So we know that mole fraction of the solute and solvent is equal, the sum of the mole fraction of solute and solvent is equal to 1. So if we are, this is the solvent, the solute would be 1 minus xb. Okay, so upon solving, we get it as P naught minus PA by P naught. This is what is called as relative lowering of vapor pressure. It is equal to the mole fraction of the solute. But this Raoult's law is applicable only for the dilute solutions. So what we are doing, we are neglecting the number of moles of the solute in the denominator. Actually, it is NB by Na. Na plus NB it should be. But because it is a dilute solution, we are neglecting the number of moles of the solute in the denominator. Okay. Next, deviations from Raoult's law. The solutions which obey Raoult's law are called as ideal solutions, and the one which do not obey, they are called as non-ideal solutions. Okay, so why are the solutions unable to obey Raoult's law? It is because once the solute and solvent are mixed, the interaction can be more or the interaction can be lesser between them. If the interaction is more, so the solute and solvent will be tending to be in the solution form itself. Okay, and when they are present in the solution form itself, the expected vapor pressure would be lesser. If the interaction is less. What is happening? You can see here. Interaction is less. So solute and solvent are vaporizing. So vapor pressure would be more. So such is called as, if the interaction is less, it is a positive deviation. If the interaction between the solute and solvent is more, it is a negative deviation. Okay. Yeah. We can see here. For the negative deviation solution, the vapor pressure expected would be lower. Okay. And delta H would be lesser, negative. All lesser only, right? And temperature change, again, it would be energy is released, delta H is negative, and temperature change when solution is formed, it would increase. Okay, what we know that whenever delta H is negative, that means it is exothermic. When delta H is positive, it is endothermic. Okay, so positive deviation solutions are endothermic. That means they absorb the heat when the solution is being formed. Okay, so example is acetone and water is an example of negative deviation. Ethanol and hexane are example of positive deviation. Yeah. So here in the form of graph, okay, you can observe this yellow line above this blue one, right? So whichever is above, if it is above, okay, yeah, you can see here. That means this is the expected, this line is the expected vapor pressure. But in actual, we are getting more. So it is positive deviation. In this case, it is expected, but we are getting less. So this is negative deviation solution. Yeah. Coming to the limitations of Rolle's law. So what are the limitations? It is applicable only for the dilute solutions, and the solute should be not acidic. Okay. Next, coming to the azeotropes. So azeotropic mixture is the one where the solution form as well as the vapor phase, both the compositions are same. Okay, that means when we are heating the solution, the solute is not separating from the solvent. They are thoroughly mixed and both are getting vaporized. Such a type of solution is called as an azeotrope. Whereas zeotropic mixtures are those, okay, which would be having, the components are having different boiling points. So please do not get confused with azeotropic and zeotropic. Azeotropic means the vapor phase is having the same composition as that of the solution. Whereas zeotropic mixtures, when they are heated, what happens? The solute and the solvent would separate off. The components, or we can say that the components are having different boiling points. So zeotropic mixtures can be separated by fractional distillation, whereas azeotropic mixtures, they can't be separated easily by fractional distillation. Yeah. Next, coming to the types of azeotropes: minimum boiling azeotrope and maximum boiling azeotrope. Okay. The boiling of the maximum azeotrope is higher than the boiling points of the constituents. Okay. When the boiling point is more than its constituents, we call it as maximum boiling. If the boiling point of the mixture is lesser than the constituents, individual constituents, we call it as minimum boiling azeotrope. Okay. Next, coming to the properties. Yeah, what are colligative properties? The properties which depend upon the number of solute particles. They are called as colligative properties. So for colligative properties, we have studied in intermediate IPE point of view. What are those? Relative lowering of vapor pressure, elevation in boiling point, depression in freezing point, and osmotic pressure. Okay. Yeah. We know that just now we have discussed relative lowering of vapor pressure is nothing but it is the ratio of lowering of vapor pressure to the vapor pressure of pure solvent. Okay, that is called as relative lowering of vapor pressure, and that is equal to the mole fraction of the solute. Okay. Next, coming to the boiling point and its elevation. Yeah, when we see the boiling point of the pure solvent is lesser when compared to the boiling point of the solution. Okay, that means suppose you are taking water and salt water. Salt water would be having more boiling point. Okay, so that is what we are saying, the boiling point has been increased. That is what is elevation in boiling point. So delta TB, you can observe here, delta TB is the difference in the boiling point of the solution and the pure solvent. Okay, that is directly proportional to the molality. Okay, sorry, molality. It is directly proportional to the molality. So when we are removing the proportionality, we get a constant, that is ebuloscopic constant or molal elevation constant. Okay, so we can expect a problem based on this. Okay, next is coming to the freezing point depression. Okay, so what is freezing point depression? When we are comparing to a solution and the solute is, sorry, solvent, water and salt water, if you consider, same thing, same example we'll take. Water would be freezing at 0 degrees, whereas salt water would be freezing at lower than 0. That means -1, -2 it can be. Okay, so what is happening? Upon adding the solute, the solution's freezing point has been decreased. So we are calling it as depression in freezing point. And that is also the difference between the freezing point of the solution and the pure solvent. That is represented as delta TF. And that is again directly proportional to the molality of the solution. So we are getting it as delta TF is.
मैडम,
yes sir.
टाइम हो गया मैडम, 4 मिनट है, दूसरा लिंक देना है.
हाँ, okay sir, ठीक है.